In 2022, the James Webb Space Telescope found something that shouldn't exist. A galaxy called Maisie's Galaxy, shining from 13.4 billion light-years away. It formed just 390 million years after the Big Bang. Here's the problem: it was already mature, making stars 100 times faster than modern galaxies. According to every model we have, Maisie's Galaxy is impossible. If you enjoy exploring the mysteries of our universe, please subscribe to our channel for more cosmic discoveries. Here's the story we've been telling for decades. After the Big Bang, the universe was simple. Just hydrogen and helium gas spreading out in the darkness. For about 100 million years, there was nothing, no stars, no light, just hydrogen clouds waiting in the cosmic dark. This period astronomers call the Dark Ages. The universe was filled with matter, but that matter hadn't yet organized itself into anything we would recognize as structure. Then, gravity slowly began its work. Tiny variations in density, some regions had slightly more matter than others, became the seeds of everything to come. Gas began falling into these denser regions. As it fell, it heated up. Eventually, after perhaps 150 million years, the first stars ignited. These first stars were nothing like our Sunday. They were massive, perhaps 100, 200, even 300 times the mass of our Sunday. They burned incredibly hot and bright, but they lived fast and died young. Within just 10 million years, many of them exploded as supernovas. When they died, they scattered newly forged elements into space. Carbon, small amounts of heavier elements created in their cores and in the violence of their explosions. This debris mixed with the primordial hydrogen and helium. New stars formed from this slightly enriched material, the second generation. These stars also lived, also died, also scattered their products into space. With each generation, the universe became chemically richer. More carbon, more oxygen, eventually nitrogen, eventually iron. But here's the critical point: this process takes time. A massive first-generation star might live 10 million years. After it explodes, it takes another 50 to 100 million years for new stars to form from the debris. Those stars live their lives, let's say another 10 to 50 million years. Then they die. Then new stars form again. By the time you reach the fourth or fifth generation of stars, the generations needed to produce significant amounts of nitrogen and other complex elements, you should be at least 500 million to 1 billion years after the Big Bang. That's the timeline. That's what the physics tells us. Galaxies themselves were supposed to follow a similar slow build process. They start small little clumps of perhaps a few million stars. These clumps merge with other clumps. Gradually, over hundreds of millions of years, they build up into the large spiral and elliptical galaxies we see in the modern universe. The early galaxies, those forming in the first few 100 million years, should be small. They should be dim. They should be irregular and chaotic, not yet settled into organized structures. They should contain only the simplest chemistry because there hasn't been time for multiple generations of stars to enrich the gas. This wasn't guesswork. This timeline had been refined over decades. It was built on solid physics, the physics of nuclear fusion, the physics of supernova explosions, the physics of how gas cools and collapses under gravity. Computer simulations that incorporated all this physics predicted what the early universe should look like. Observations from the Hubble Space Telescope looking at galaxies from 1 to 2 billion years after the Big Bang seemed to confirm this picture. Everything fit together. The standard model of cosmology, known technically as lambda CDM, successfully explained the large-scale structure of the universe. The patterns in the cosmic microwave background radiation, the distribution of galaxies, the expansion rate of the universe. It was one of the triumphs of 20th century physics. And then James Webb looked at the earliest times, the first 300 to 600 million years after the Big Bang, and found galaxies that violated every expectation. Maisie's galaxy has nitrogen at 390 million years. That's impossible under the standard timeline. You simply cannot run through enough stellar generations to produce nitrogen in that time. It's like planting a seed in the morning and harvesting a 100-year-old oak tree by lunchtime. The process that should take billions of years happened in hundreds of millions. But Maisie's wasn't alone. James Webb kept finding them, galaxy after galaxy from the cosmic dawn, all showing properties they shouldn't have. all challenging the careful timeline we'd constructed. Maisie's galaxy wasn't a fluke. James Webb kept finding them. By 2023, astronomers had catalogued dozens of these impossible early galaxies, all from the first 300 to 600 million years after the Big Bang, all impossibly bright, all making stars at ridiculous speeds, all showing chemical complexity that shouldn't exist yet. Let me give you some specific examples. There's a galaxy designated Glass Z13. It existed just 320 million years after the Big Bang. It's forming stars at a rate of about 20 solar masses per year. That means every year, it's creating the equivalent of 20 stars like our Sunday. For comparison, our Milky Way galaxy with its hundreds of billions of stars forms only about 1 to 2 solar masses worth of new stars per year. This tiny early galaxy is making stars 10 to 20 times faster than our entire galaxy. And it's doing this when the universe barely had time to settle down from the Big Bang. Then there's CERS 93316. This galaxy is even more extreme. It appears to be forming stars at a rate of over 100 solar masses per year, 100 times what our galaxy manages. And it's doing this at cosmic dawn, when galaxies should barely be getting started. The pattern was undeniable. Some of these early galaxies were so bright that when scientists first saw the data, they thought the instruments were malfunctioning. The brightness levels didn't make sense. A typical galaxy from 500 million years after the Big Bang was predicted to have a certain luminosity based on our models. The galaxies James Webb found were 10 to 100 times brighter than those predictions. 10 to 100 times. That's not a small discrepancy you can explain away with measurement uncertainty. That's a fundamental problem with the model. And it wasn't just brightness. The galaxies were surprisingly organized. We expected early galaxies to be messy, chaotic, irregular blobs of stars still in the process of settling down. Instead, James Webb found galaxies with clear structure. Some even showed signs of spiral arms or organized disks. They looked evolved, mature, settled adjectives that shouldn't apply to galaxies this young. The chemical enrichment was perhaps the most troubling piece. Spectroscopy, breaking down the light from these galaxies into its component wavelengths, revealed the presence of elements that required time to build up. Not just nitrogen, but also oxygen in significant quantities. Carbon, even traces of heavier elements. Remember, the timeline you need stars to form, live, and die to create these elements. You need that to happen multiple times with each generation, enriching the gas a bit more. The standard models said this process would take at least 500 million to 1 billion years to produce the levels of enrichment Webb was seeing. But here were galaxies showing that enrichment at 300 million, 350 million, 400 million years. The timeline was compressed by a factor of 2 or 3 or more. Supermassive black holes added another layer to the puzzle. At the centers of most large galaxies sit supermassive black holes, objects with masses of millions or billions of times our sun's mass. We thought these black holes grew gradually, starting from stellar mass black holes, perhaps 10 to 100 solar masses, and slowly accumulating matter over time. James Webb found supermassive black holes that already had masses of millions of solar masses at just 500 million years after the Big Bang. Some appeared to have billions of solar masses. The growth rate required to go from stellar mass black holes to these monsters in such a short time exceeded what we thought was physically possible. Black holes can only grow so fast. There are limits set by the physics of how matter falls into them. Yet there they were. Massive black holes at cosmic dawn, already fully formed, already powering the bright cores of their host galaxies. By late 2023 and into 2024, the astronomy community was in genuine crisis mode. Major conferences devoted entire sessions to the early galaxy problem. Papers with titles like The Crisis in Cosmology and Rethinking Galaxy Formation began appearing. This wasn't about one weird observation. This was about a systematic failure of our models to predict what the early universe actually looked like. Some scientists initially hoped the observations were wrong. Maybe James Webb was miscalibrating distances. Maybe the very red light from these galaxies, stretched by the expansion of the universe, was being misinterpreted. Maybe dust in the galaxies was making them appear brighter than they really were. But as more data came in, those hopes faded. Multiple independent teams analyzed the same galaxies and got the same results. The distances were confirmed. The brightness was real. The chemistry was real. The observations were solid, which meant the problem was with the theory. The standard model of cosmology lambda CDM wasn't wrong exactly. It still explained the modern universe beautifully, but it was incomplete. It was missing something crucial about how the early universe worked. Some process, some mechanism, some piece of physics that made the early universe far more efficient at building galaxies than anyone had anticipated. Every new image from James Webb added another crack in the foundation, and scientists were scrambling to figure out what needed to be fixed. Let me take you inside one of these early galaxies. You're 13 billion light-years away looking at a galaxy when the universe was 400 million years old. It's small, maybe 500 light-years across. To put that in perspective, our Milky Way is 100,000 light-years across. This galaxy is 1/200th the size. Imagine our entire galaxy compressed down to the size of a single city, and you get a sense of the scale, or rather the lack of scale. These early galaxies are tiny, but they're blazing. Stars are forming at a rate of 100 solar masses per year. Our Milky Way, remember, forms about 1 to 2 solar masses per year. This tiny galaxy is making stars 50 to 100 times faster than our entire galaxy. The density of star formation is beyond anything we see in the modern universe. Think of it this way: in our galaxy, stars are spread out. There's a lot of empty space between them. The average distance between stars in our solar neighborhood is about 4 light-years. In these early compact galaxies, stars are packed much closer together. The entire galaxy is smaller than the distance between some star systems in the Milky Way. And within that compressed volume, star formation is happening at a frantic pace. The stars themselves appear to be different. In our galaxy, when a cloud of gas collapses to form stars, you get a range of masses. Most are small red dwarfs with a fraction of the Sun's mass. Some are medium-sized, like our Sunday. A few are massive 10, 20, 50 times the Sun's mass. But in these early galaxies, the ratio seems skewed toward more massive stars. This makes sense. In a way, the gas is hotter, the clouds are more turbulent, the conditions favor the formation of bigger stars. And bigger stars burn brighter and hotter, which partly explains why these galaxies are so luminous despite their small size. But massive stars also die quickly. A star with 50 times the Sun's mass might live only a few million years before exploding as a supernova. So these galaxies are not just forming stars rapidly, they're also destroying them rapidly. It's a cycle of birth and death happening at breakneck speed. The supernovas themselves play a crucial role. When a massive star explodes, it doesn't just scatter elements into space, it also drives powerful shockwaves through the surrounding gas. These shockwaves can compress other gas clouds, triggering new rounds of star formation. So the death of one generation of stars directly triggers the birth of the next generation. In modern galaxies, this process is relatively sedate. In these early compact galaxies, it appears to be a runaway chain reaction. Star formation, triggering explosions, triggering more star formation. The galaxy is a roiling, churning, violent place, a cosmic storm of creation and destruction happening simultaneously. And somehow, out of this chaos, elements are being forged at an incredible rate. Let's talk about that nitrogen. Nitrogen is interesting because it's hard to make. It requires a specific sequence of nuclear reactions that happens in the cores of certain types of stars. Carbon and oxygen can be made in the first few generations of stars relatively easily. Nitrogen requires more steps, more generations, more time. Or at least that's what we thought. The presence of nitrogen in Myces's galaxy, and others like it, suggests that multiple stellar generations have already come and gone. First-generation stars formed created carbon and oxygen and died. Second-generation stars formed from that enriched material created more carbon and oxygen plus some nitrogen and died. Third-generation stars are now forming, and we're seeing their light enriched with all these elements. All of this in 390 million years. The efficiency is staggering. It's like the universe found a shortcut, a way to speedrun through the process that should take billions of years. Every available gas cloud is being used. Every stellar generation is enriching the gas as much as possible. There's no waste, no downtime, no inefficiency. Modern galaxies are lazy by comparison. In the Milky Way, only about 1% of the available gas is actually forming stars at any given time. The rest just sits there waiting. But these early galaxies appear to be converting 10, 20, even 30% of their gas into stars. They're operating near the theoretical maximum efficiency. Why? What's driving this efficiency? Scientists have a few ideas, but no definitive answer. Maybe the gas in the early universe was easier to collapse into stars hotter, denser, more susceptible to gravitational pull. Maybe the first supermassive black holes played a role, their energy output somehow regulating and enhancing star formation rather than shutting it down. Maybe there were primordial black holes. Black holes formed directly from density fluctuations in the early universe, rather than from stellar collapse that seeded galaxy formation and accelerated the process. Or maybe there's physics we don't understand yet. Some process happening in the extreme conditions of the early universe that simply doesn't occur anymore. What we do know is this: these galaxies represent a mode of galaxy formation that no longer exists in the universe. They're not just young versions of modern galaxies, they're fundamentally different. They operated by different rules, achieved different efficiencies, and evolved in ways we're only beginning to understand. And they challenge everything we thought we knew about how complexity emerges from simplicity in the cosmos. Here's the timeline problem in detail. Big Bang happens at time 0. The universe is unimaginably hot and dense, filled with a soup of elementary particles. It begins expanding and cooling. After about 380,000 years, the universe has cooled enough for electrons and protons to combine into neutral hydrogen atoms. This moment, called recombination, is important because it's when the universe becomes transparent to light. Before this, photons couldn't travel far without scattering off free electrons. After this, light can travel freely. This is the light we now see as the cosmic microwave background radiation. But the universe is still dark. There are no stars, yet no sources of visible light. Just neutral hydrogen gas slightly clumped in some regions and slightly diluted in others, floating in the expanding cosmos. The Dark Ages begin. 100 million years of darkness. Gravity is working during this time, pulling gas into the denser regions, but nothing is glowing yet. The universe is waiting. Then around 100 million to 150 million years after the Big Bang, the first stars ignite. These population 3 stars, so named because they're the third type, astronomers theorized about, even though they formed first, are massive and metal-free. Metal-free, in astronomical terms, means they contain only hydrogen and helium, the elements created in the Big Bang itself. Let's say the first stars form at 100 million years. They're huge 100 to 300 solar masses, and they burn hot and fast. Within 10 million years, they explode as pair instability supernovas, completely destroying themselves and scattering their newly forged elements into space. So, at 110 million years, the first heavy elements appear in the universe: carbon, oxygen, some silicon, magnesium, sulfur, the products of nuclear fusion, in those massive stellar cores. Now, gas clouds have a tiny bit of metal in them. This matters because metals help gas cool more efficiently, and cooler gas can collapse more easily to form stars. So the second generation of stars can form a bit more readily. Let's say second generation stars start forming at 150 million years. These stars have a range of masses, some massive, some medium-sized. They live for 10 to 50 million years depending on their mass. The most massive ones explode first, enriching the gas further. At 200 million years, the third generation begins forming. The gas is now noticeably enriched with carbon and oxygen. Nitrogen is starting to appear, created in intermediate mass stars through a process called the CNO cycle. But nitrogen levels are still low. By 250 million years, we're into the fourth generation. Nitrogen levels are becoming significant. The gas has cycled through enough stellar generations that complex chemistry is starting to build up. At 300 million years, 350 million years, we should be seeing galaxies with moderate enrichment. Some nitrogen, decent amounts of carbon and oxygen, but still clearly young, still in the early stages of chemical evolution. This is the timeline the standard models predicted, and it made sense based on the physics. Each stellar generation needs time to form, time to live, time to die, and time for the debris to mix back into the gas before the next generation can form. But Maisie's galaxy has significant nitrogen at 390 million years, not trace amounts, significant amounts visible in the spectroscopic analysis. That suggests at least 4 or 5 stellar generations have already occurred, which means the timeline compressed by a factor of 2 or more. Each generation somehow happened faster than the physics seems to allow. Or there's another explanation, maybe the very first stars were even more massive than we thought, and they died even faster. Maybe some were 1,000 solar masses living only 1 or 2 million years before exploding. That could compress the timeline. But there's a problem with that idea. When very massive stars die, they produce specific patterns of elements, lots of oxygen relative to carbon, for example. We don't see those patterns in the early galaxies. The element ratios look more like what you'd get from a mix of stellar masses, not exclusively supermassive stars. So we can't easily explain the rapid enrichment by simply making the first stars bigger. Maybe multiple generations overlapped in time. Instead of generation 1 forming, living, dying, then generation 2 forming. Maybe generation 2 started forming, while generation 1 was still around. This could speed things up somewhat, but there are limits. You need the gas from generation 1 supernovas to actually reach the regions where generation 2 is forming. That takes time. Gas has to travel through space, and space is big even in these compact galaxies. Or maybe the star formation efficiency was so high that each generation used almost all available gas, leaving enriched material immediately available for the next generation. No wasted gas, no delays. But even with perfect efficiency, you still have the fundamental limit. Stars need time to live and die. A star that's going to produce nitrogen needs to go through its entire life cycle. For most stars, that's millions to hundreds of millions of years. Unless, what if there were exotic processes we haven't considered? What if, in the extreme conditions of the early universe, there were ways to create elements that don't exist anymore? Primordial pathways to nucleosynthesis that we've never observed because they require conditions we can't replicate. Some physicists have suggested that collapsing gas clouds in the early universe might have been so dense that nuclear reactions could occur in the clouds themselves before stars even formed. Direct fusion in the interstellar medium. This would be unprecedented. We've never seen this in the modern universe, but maybe it happened at cosmic dawn. Others have proposed that the first black holes, if they were spinning rapidly, could have had powerful jets that drove nuclear reactions in the surrounding gas. Black hole jets accelerating particles to such high energies that fusion occurred in the jet itself. These are speculative ideas, but they're being seriously discussed because the timeline problem is so severe. The bottom line, we're not talking about tweaking a number here or there. We're talking about compressing what should be a billion-year timeline into 300 million years. That's not a small adjustment. That's a fundamental rethinking of how fast the universe can build complexity. And the implications go beyond just early galaxies. This timeline compression affects our understanding of when life could have emerged in the universe, when the first Earth-like planets could have formed, when the universe became chemically rich enough to support the kind of complex chemistry that leads to biology. If the universe was racing through its early development at 3 times the speed, we thought everything else has to be reconsidered too. The standard model of cosmology has a name, lambda CDM. Lambda refers to dark energy, the mysterious force causing the universe's expansion to accelerate. CDM stands for cold dark matter, the invisible matter that makes up most of the mass in the universe. Lambda CDM has been remarkably successful. It emerged in the 1990s and was refined through the 2000s as better data came in. It successfully predicted the patterns we see in the cosmic microwave background, the afterglow of the Big Bang. It explained the large-scale structure of the universe, why galaxies are distributed in filaments and sheets rather than uniformly. It accounted for the expansion rate of the universe, both its current value and how it has changed over cosmic history. For the local universe, the universe within a few billion light years of us, lambda CDM works beautifully. Its predictions match observations to remarkable precision. But lambda CDM makes specific predictions about the early universe. And this is where James Webb has exposed its limitations. Lambda CDM says that structure formation in the early universe should be hierarchical. Small things form first, then merge into larger things. Tiny dark matter halos, clumps of dark matter held together by gravity, form first. Gas falls into these halos. Stars form in the gas. These star-forming halos merge with other halos, building up progressively larger structures. Early galaxies in this picture should be small and dim. They should be irregular, not yet settled into organized structures. They should be relatively inefficient at forming stars, because the first supernovas should blow a lot of gas out of the shallow gravitational wells of these small systems. Galaxy growth should accelerate over time as halos get bigger and their gravity gets stronger, allowing them to hold onto gas better and form stars more efficiently. So, galaxies at 1 billion years after the Big Bang should be more massive and brighter than galaxies at 500 million years, which should be more massive and brighter than galaxies at 300 million years. That's the prediction. The reality is different. James Webb finds numerous galaxies at 300 to 600 million years that are as bright as, sometimes brighter than, galaxies at 1 to 2 billion years. The predicted progression of brightness with time is not what we observe. The model predicted that galaxies with stellar masses of 10 billion solar masses shouldn't exist until at least 1 billion years after the Big Bang. James Webb found several such massive galaxies at 700 to 800 million years. Some candidates might be even earlier. The gap between prediction and observation is not subtle. Predicted masses might be 10 billion solar masses at 1 billion years. Observed masses are 10 billion solar masses at 700 million years. The universe built massive galaxies 30% faster than the model said it could. That might not sound like much, 30%, but in cosmology that's huge. These models are based on well-established physics. A 30% discrepancy suggests something fundamental is missing. One possibility is that the initial density fluctuations in the universe, the tiny variations in density that seeded all structure formation, were larger than we thought. If some regions had more matter, then our models assumed they could collapse faster and form galaxies earlier. But there's a problem with this explanation. We can measure the initial density fluctuations directly by looking at the cosmic microwave background. The patterns in that radiation tell us exactly how strong the density variations were in the early universe. And those measurements don't support having fluctuations large enough to explain what James Webb sees. Another possibility is that dark matter behaves differently than we assumed. Standard lambda CDM assumes cold dark matter particles that move slowly and clump efficiently. Maybe dark matter is slightly warmer or interacts with itself in ways we haven't accounted for, changing how quickly structure forms. But again, this runs into problems. If you change dark matter properties to make early galaxies form faster, you often break the model's predictions for the modern universe, which are otherwise accurate. A third possibility is that star formation efficiency in the early universe was much higher than we thought. Maybe the physical processes that convert gas into stars work differently under early universe conditions. Maybe the gas was easier to collapse, or the first supernovas were less effective at blowing gas out of galaxies, allowing more gas to remain available for continued star formation. This is promising, but it requires us to understand why star formation would be more efficient then than now. What changed? What mechanism operated in the early universe that doesn't operate anymore? The supermassive black hole problem adds another layer of complexity. Black holes grow by accreting matter, gas and dust falling into them. There's a limit to how fast they can grow, called the Eddington limit. When matter falls into a black hole, it heats up and emits radiation. If the radiation becomes too intense, it pushes away additional infalling matter, limiting the growth rate. At the Eddington limit, a black hole can roughly double its mass every 50 million years. Starting from a stellar mass black hole of 100 solar masses at 200 million years after the Big Bang, growing at the Eddington limit continuously, you could reach about 1 million solar masses by 500 million years. James Webb finds black holes of 100 million to a billion solar masses at 500 million years. That's 100 to 1,000 times more massive than Eddington limited growth would allow. So either black holes were growing faster than the Eddington limit, which requires special circumstances, like having a constant supply of cold gas falling in from all directions, or they started much more massive. If they started more massive, where did those massive seeds come from? One idea is primordial black holes. Black holes form directly from density fluctuations in the first moments after the Big Bang, not from stellar collapse. These could have masses of thousands or even millions of solar masses right from the start. But primordial black holes are theoretical. We've never confirmed their existence. And if they exist and are common enough to seed all the early supermassive black holes we see, that has other implications for cosmology that need to be worked out. The point is, every explanation for the early galaxy observations seems to require adding something new to the model. New physics, new initial conditions, new types of objects. Lambda CDM, as currently formulated, can't explain what James Webb sees. That doesn't mean Lambda CDM is wrong. It means it's incomplete. The model captures much of reality, but it's missing pieces that were important in the early universe and became less important later on. Scientists are now working intensely on extended versions of Lambda CDM, models that include primordial black holes, models with modified dark matter, models with enhanced early star formation efficiency, models with complex feedback processes between black holes and star formation. Some of these models show promise. They can reproduce some of the James Webb observations while still matching the cosmic microwave background data and the large-scale structure of the modern universe. But we don't yet have a single coherent model that explains everything. We're in a period of scientific uncertainty and creative ferment. Multiple teams are exploring different directions, and it will take time, years probably, for consensus to emerge about which direction is correct. This is how science actually works. A well-established model encounters observations it can't explain. Scientists propose extensions and modifications. They test these new models against additional data. Gradually, a new consensus forms around the models that work best. It's messy and uncertain in the moment, but it's also exciting. We're watching paradigm shift in real time. Some observations suggest the universe might have a preferred direction. In 2013, a group of physicists analyzed the rotation of more than 15,000 galaxies. They found something unexpected. Galaxies showed a slight tendency to rotate one direction more than the other. It wasn't a huge effect, about 7% more galaxies spinning one way versus the other way, but it was statistically significant. This shouldn't happen in a truly isotropic universe. Isotropy is the principle that the universe looks the same in all directions. If you stand at any point in space and look around, the large-scale properties should be identical no matter which way you look. No preferred directions, no special axes. Isotropy is a fundamental assumption of modern cosmology. It's built into Lambda CDM. If isotropy is violated, it means the universe has structure at the largest scales that we haven't accounted for. The galaxy rotation study has been debated. Some follow-up studies found similar effects, others didn't. The jury is still out on whether the effect is real or a statistical fluke. But it's not the only hint of large-scale asymmetry. The cosmic microwave background, the radiation left over from the Big Bang, also shows subtle anomalies. There's what cosmologists call the axis of evil, a somewhat tongue-in-cheek name for an apparent alignment of temperature patterns in the CMB along a particular axis in space. Again, this shouldn't exist in a perfectly isotropic universe. These anomalies are small. They could be statistical flukes or systematic errors in measurement. But if they're real, they suggest the universe is not perfectly uniform at the largest scales. And that raises an interesting question. If the universe has a preferred axis, what could cause that? One possibility, and I want to emphasize this is highly speculative, is that we're inside a black hole. The idea works like this. In standard general relativity, when matter collapses into a black hole, it forms a singularity, a point of infinite density, where the laws of physics break down. But physicists have long suspected that quantum effects prevent true singularities from forming. When you try to combine quantum mechanics with general relativity, something we don't yet know how to do properly, the equations suggest that the collapsing matter might not reach infinite density. Instead, at extremely high densities, quantum effects could create a kind of repulsive force that halts the collapse and reverses it. The collapse would turn into an expansion. From the outside, this would still look like a black hole. Nothing can escape across the event horizon. But from the inside, the reversal would look like an explosion, a sudden expansion from a point of extreme density. In other words, it would look like a Big Bang. This idea has been explored by several physicists, notably Lee Smolin and Nikodem Poplawski. In their models, our Big Bang might actually be the interior of a black hole in a parent universe. The expansion we see as the universe getting bigger is what the bounce looks like from inside. If this is true, it could explain a preferred axis. Black holes can rotate. If our universe is inside a rotating black hole, that rotation could impart a preferred direction to space inside. The axis of rotation becomes a special axis breaking perfect isotropy. It's an elegant idea, but it's also untestable in the conventional sense. We can't look outside our universe to see if we're inside a black hole. We can't run experiments that would confirm or rule out this scenario. What makes the idea scientifically interesting is that it makes predictions. If we're inside a rotating black hole, we should see specific patterns of anisotropy, particular types of preferred directions and asymmetries. These can be compared against the observations of galaxy rotation and CMB patterns. So far, the match is intriguing but not definitive. The data is consistent with the hypothesis but doesn't strongly favor it over other explanations for the anomalies. Now, if our universe could be inside a black hole, that raises another possibility. Maybe every black hole contains a universe. Think about what that means. Our Milky Way galaxy contains roughly 100 million stellar mass black holes formed from collapsed stars. It also contains one supermassive black hole at its center, 4 million times the mass of the Sunday. If each of those black holes contains a universe, that's 100 million universes nested inside our galaxy alone. Each of those universes might contain its own galaxies, its own black holes, each containing more universes, and so on infinitely. The observable universe contains roughly 40 billion galaxies. Each galaxy likely contains millions of black holes. That's an almost incomprehensible number of potential nested universes. And it goes the other way too. If our universe is inside a black hole, that black hole exists in a parent universe. That parent universe might also be inside a black hole in a grandparent universe. The nesting could extend infinitely in both directions. Infinite layers of universes within universes, turtles all the way down and all the way up. This is what's called cosmological natural selection or fecund universes. Lee Smolin developed this idea in the 1990s. The proposal is that universes reproduce through black hole formation. The physical constants and laws of physics in each baby universe might be slightly different from the parent, determined by the conditions of the black hole that spawned it. Over time, this could lead to a kind of evolution. Universes with physical constants that favor black hole formation would produce more baby universes passing on their constants. Universes with constants that inhibit black hole formation would produce fewer offspring. Eventually, the multiverse would be dominated by universes whose constants are tuned to maximize black hole production. Interestingly, our universe does seem to be quite good at making black holes. If you tweaked the fundamental constants, the strength of gravity, the mass of the electron, the strength of the strong nuclear force, even slightly, you'd often get a universe that makes far fewer black holes or no black holes at all. Is that a coincidence? Or are we living in a universe descended from a long line of black hole-producing ancestors? It's a beautiful idea, but it remains firmly in the realm of speculation. We have no way to confirm that black holes contain universes. We have no way to measure the physical constants of any universe other than our own. The hypothesis is scientifically interesting. It's not nonsense. It's based on plausible extensions of known physics, but it's not testable with current technology. Why bring it up at all then? Because it illustrates how deep the mysteries go. James Webb shows us that our understanding of the early universe is incomplete. That's a specific scientific problem that will eventually be solved with better observations and refined models. But lurking behind that problem are deeper questions. Why does the universe have the laws it has? Why are the constants tuned to allow complexity? Is our universe part of a larger structure we can't see? These questions might always remain beyond our ability to answer definitively, but they're worth asking. They remind us that science is not just about finding answers. It's about expanding the space of questions we know how to pose. And they remind us that the universe or multiverse might be far stranger than we can imagine from our limited vantage point. Let's ground ourselves. What have we actually learned? First, the early universe was far more dynamic and efficient than our models predicted. Galaxies formed faster, brighter, and more organized than we thought possible. Stars formed at incredible rates. Chemical enrichment happened in hundreds of millions of years rather than billions. The universe was in a hurry. Second, our current cosmological model is incomplete. Lambda CDM works beautifully for the modern universe, but fails for the early universe. Something is missing, some physics, some process, some mechanism that was important in the first few 100 million years and became less important later. Third, we're in a moment of genuine scientific uncertainty. Multiple explanations are being explored. Primordial black holes, modified dark matter, enhanced star formation. Each has strengths and weaknesses. We don't yet know which direction will prove correct. Fourth, some radical ideas like nested universes inside black holes are being discussed seriously, not because there's strong evidence for them, but because they're the kind of ideas you consider when conventional approaches aren't working. But here's the most important thing: this is how science actually works. Science is not a collection of facts. It's a process, a method of engaging with the unknown. You make observations, you build models to explain those observations. You test the models with new observations. When the observations don't match the predictions, you revise the models. Sometimes the revisions are small. You tweak a parameter here, adjust an assumption there, and the model works again. But sometimes the revisions are large. Sometimes you have to rethink fundamental assumptions. Sometimes you have to acknowledge that your beautiful, elegant model is missing something crucial. This is one of those times. The history of cosmology is full of these moments. In the 1920s, Edwin Hubble discovered that the universe is expanding. This was a shock. Einstein himself had assumed the universe was static and had added a cosmological constant to his equations to keep it from collapsing. When Hubble showed the universe was actually expanding, Einstein called the cosmological constant his biggest blunder. Except it wasn't a blunder. In the late 1990s, astronomers discovered that the universe's expansion is accelerating. This required bringing back the cosmological constant, now reinterpreted as dark energy. Einstein's supposed mistake turned out to be necessary, after all. In the 1930s, Fritz Zwicky noticed that galaxies in clusters were moving too fast. According to the visible matter, the clusters should fly apart. But they didn't. Zwicky proposed the existence of dark matter, invisible matter, providing extra gravity to hold the clusters together. The idea was largely ignored for decades. Then in the 1970s, Vera Rubin measured the rotation speeds of stars in galaxies and found the same problem. Stars far from the galactic center were moving too fast. Dark matter became unavoidable. Now we know that dark matter makes up about 85% of the matter in the universe. Most of the universe is invisible to us. That was a humbling realization. The point of these examples is this cosmology has repeatedly discovered that the universe is stranger than we thought. Each time there was a period of confusion and debate. Each time, eventually new observations and new theoretical work converged on a new understanding. The field moved forward. We're in another such period now. The James Webb observations have opened a gap between prediction and reality. Scientists are working to close that gap. It will take time. There will be false starts and dead ends. But eventually we'll have a better model, and that better model will inevitably have its own limitations. It will explain the early universe, but then some future telescope will find something it can't explain. And the process will begin again. This isn't a flaw in science. It's a feature. Science doesn't claim to have final answers. It claims to have a method for getting progressively less wrong. Each generation of scientists builds on the work of previous generations, correcting errors, refining models, expanding the domain of what we understand. From our limited human perspective, this can feel frustrating. We want certainty. We want to know the truth. But the universe doesn't owe us simple truths. It is what it is, regardless of our ability to understand it. What's remarkable is that we can understand as much as we do. We're biological creatures evolved to survive on the African savanna, dealing with medium-sized objects moving at medium speeds. We have no evolutionary reason to understand cosmology, or quantum mechanics, or relativity. These are domains utterly removed from the environment that shaped our brains. Yet we've developed mathematics and physics and the scientific method, and these tools let us figure out what happened 13 billion years ago and what will happen trillions of years in the future. We've mapped the large-scale structure of the universe. We've detected gravitational waves from colliding black holes. We've built telescopes that can catch photons that have been traveling since the cosmic dawn. That's extraordinary. And we've done it knowing that each answer leads to new questions. Knowing that we'll never have complete knowledge. Knowing that uncertainty is permanent. Being comfortable with uncertainty is one of the hardest things humans have to learn. We evolved to seek patterns, to make quick judgments, to feel confident, even with limited information. These traits helped our ancestors survive, but they're obstacles to scientific thinking. Science requires the opposite: being comfortable saying, "I don't know." Being willing to hold multiple hypotheses simultaneously without committing to any of them prematurely. Being open to the possibility that you're wrong even about things you've believed for years. This is difficult, but it's also liberating. Once you accept that uncertainty is okay, that not knowing is not a failure, you're free to explore. Free to ask wild questions. Free to consider ideas that might seem crazy at first, but turn out to contain profound insights. The James Webb observations have pushed cosmology into this space. We don't know exactly how to explain what we're seeing. That's uncomfortable, but it's also exciting. It means there's genuine discovery ahead. It means the next few years will bring surprises. And it means we get to participate in one of humanity's great adventures, the quest to understand the universe we inhabit. You are standing on a planet that's 4.5 billion years old. That planet orbits a star that's 4.6 billion years old. That star is one of roughly 400 billion stars in a galaxy that's 13.6 billion years old. That galaxy is one of roughly 40 billion galaxies in the observable universe. The observable universe is 13.8 billion years old, expanding at an accelerating rate, filled mostly with things we can't see. Dark matter and dark energy making up 95% of its content. And you might be inside a black hole in a universe that might be one of infinite universes nested inside each other like Russian dolls. By any measure, you are vanishingly small. Your entire species has existed for roughly 300,000 years. That's 0.002% of cosmic history. Your personal lifespan is a fraction of that fraction. On a cosmic timeline, you barely register, and yet, you are made of atoms, forged in stars. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was created in the cores of stars that lived and died billions of years ago. You are literally made of stardust. That's not a poetic metaphor. It's a literal fact. When a massive star reaches the end of its life, it fuses lighter elements into heavier ones. In its core, carbon from helium, oxygen from carbon, silicon, sulfur, magnesium, all forged in the intense heat and pressure of stellar cores. Iron forms in the final stages right before the star explodes. When the star goes supernova, it scatters these elements across space. They mix with hydrogen and helium, forming new clouds of gas. Those clouds collapse to form new stars and planets. The heavy elements become the rocky planets. They become the molecules that make life possible. The atoms in your body have been on a journey. They were created in stellar cores billions of years ago. They drifted through space for millions of years. They were part of the molecular cloud that collapsed to form the Sun and Solar System 4.6 billion years ago. They were part of the dust and gas that clumped together to form Earth. They cycled through rocks, through water, through the atmosphere, through countless living organisms over billions of years. And now, for a brief moment in cosmic time, they're arranged in a pattern that thinks that wonders that can look up at the night sky and contemplate its own origin. You are the universe examining itself. You are matter that has become conscious of matter. You are stardust that has learned to think. That's profound. Your species went from ignorance to measuring the universe in just a few centuries. 400 years ago, we didn't know the planets orbit the Sun. We thought the Earth was the center of everything. We thought the Milky Way was the entire universe. 100 years ago, we learned that galaxies exist beyond our own. That the universe is vastly larger than we'd imagined. 90 years ago, we discovered the universe is expanding. 60 years ago, we detected the cosmic microwave background and confirmed the Big Bang theory. 35 years ago, we launched the Hubble Space Telescope and began seeing the universe in unprecedented detail. 2 years ago, we turned on James Webb and began seeing the cosmic dawn. In the span of a single human lifetime, we've gone from barely knowing that other galaxies exist to seeing galaxies from when the universe was 2% of its current age. We've gone from speculation about the Big Bang to measuring its afterglow with exquisite precision. We've gone from wondering if the universe had a beginning to mapping its entire history. That's extraordinary progress for a species that only learned to write 6,000 years ago. And it's not just astronomy. In the same time frame, we figured out the structure of DNA, split, the atom discovered, antibiotics eradicated, smallpox put humans on the moon, built quantum computers, detected gravitational waves, and created a global communications network that connects billions of people. We're capable of remarkable things when we work together and build on each other's knowledge. But here's the deeper point: the fact that we can do this at all is astonishing. You're a collection of atoms governed by the laws of physics. Those laws are mathematical. The universe operates according to equations, and somehow you, a particular arrangement of atoms, can understand those equations. You can look at the universe and decode its rules. Why? Why should the universe be comprehensible to us? There's no obvious reason. The universe could have been chaotic, following no consistent laws. It could have followed laws too complex for human minds to grasp. It could have been simple, but made our brains too limited to figure it out. Instead, the universe follows laws that are mathematical, and human minds are capable of doing mathematics. There's a match between the structure of reality and the structure of thought. That's not something we should take for granted. Some physicists have argued that this unreasonable effectiveness of mathematics is one of the deepest mysteries. Why does abstract reasoning work so well for understanding physical reality? Why can we sit in offices with blackboards and figure out what's happening in the cores of stars or the event horizons of black holes? No one knows. It's a fortunate fact that makes science possible. Without it, we'd be forever blind to the workings of the cosmos. So yes, you're small. You're fleeting. You occupy a tiny corner of space for a brief moment of time, but you're also part of something extraordinary. You're part of the universe's process of self-discovery. You're a node in a web of consciousness that spans the entire planet, billions of humans each contributing their piece to humanity's collective understanding. Every time someone looks through a telescope, analyzes data from James Webb, runs a simulation of galaxy formation, or simply looks up at the night sky and wonders, they're participating in this grand project. The project of understanding where we came from and where we're going. The project of making sense of existence itself. And the project is far from complete. The James Webb observations are a reminder of how much we still don't know. But that's not discouraging. That's exciting. It means there's still territory to explore, still mysteries to unravel, still surprises waiting. Your generation gets to participate in this exploration. You get to live in a time when genuine paradigm shifts are happening, when cosmology is being rewritten, when the boundaries of the known are expanding. That's a gift. You didn't choose to exist. You didn't choose when or where to be born. But you exist now, in this moment, when humanity is looking deeper into space and time than ever before. When we're finding things that challenge everything we thought we knew, you get to be part of the species that figured this out. That's worth something. The universe is under no obligation to make sense to you. It doesn't owe you simple answers. It doesn't owe you explanations that fit comfortably within human intuition. It is what it is, following its own logic, operating by its own rules, and yet it gives us glimpses. Ancient light arrives after billion-year journeys. Galaxies that shouldn't exist appear in our telescopes. Equations hint at hidden dimensions and nested realities. The universe reveals itself slowly, piece by piece, each revelation raising new questions. This is not a flaw. This is the beauty of it. If we knew everything, if the universe held no more mysteries, if every question had a final answer, what would be left? What would pull us forward? What would fill us with wonder? Mystery is not the enemy of understanding. Mystery is what makes understanding worthwhile. Think about what we've discovered in just the last century. We've learned that space and time are flexible, that mass and energy are interchangeable, that empty space has energy, that most of the universe is invisible, that the past is visible in the light reaching us from distant galaxies. Each of these discoveries was shocking when first proposed. Each contradicted common sense. Each required letting go of comfortable assumptions about how reality works. And each opened up vast new territories of mystery. Relativity gave us black holes and the Big Bang. Quantum mechanics gave us particles that are also waves and measurements that affect reality. Dark matter and dark energy revealed that we don't even know what most of the universe is made of. Every answer births a dozen new questions. That's not a sign that we're doing something wrong. That's a sign that reality is deep, that there are always more layers to uncover, that the project of understanding never ends. The James Webb discoveries are the latest chapter in this story. They've shown us that the early universe was stranger than we predicted. They've revealed gaps in our models. They've pushed us to consider radical ideas about the nature of reality itself. But they haven't given us final answers. They've given us better questions. How did galaxies form so fast? What mechanisms drove the efficiency we see at cosmic dawn? Are there processes in the early universe that no longer operate? What role did the first black holes play? Is there physics beyond lambda CDM, that the first beyond lambda CDM, that the physics beyond? We need to discover, and beyond those specific questions, are we inside a black hole? Do black holes contain universes? Is our universe one of infinite nested realities? Is there a multiverse? Some of these questions might be answerable. With better telescopes, more data, refined theories, we might figure out what was happening in the early universe. We might develop a new cosmological model that explains everything James Webb sees. But some questions might be permanently beyond our reach. We can't see outside our universe to check if we're inside a black hole. We can't access other universes to measure their physical constants. We can't run experiments on the multiverse. There might be truths about reality that we can never confirm, facts that are forever beyond the horizon of what's knowable, and that's okay. Not every question needs an answer. Some questions are valuable simply for being asked. They expand our sense of what's possible. They challenge our assumptions. They remind us that reality is stranger than we imagine. The history of science is full of confident assertions that turned out to be wrong. Newton's absolute space and time, the luminiferous ether, the steady-state universe, the impossibility of black holes, continental drift being impossible, atoms being the smallest particles. Each generation of scientists thinks they've nearly figured everything out. Each generation is humbled by new discoveries, so we should approach our current understanding with humility. Lambda CDM is our best model, but it's not the final word. The nested universe hypothesis is intriguing, but it's speculative. Dark matter and dark energy are placeholders for things we don't really understand. We know a lot, but we also know that we don't know a lot, and there are probably things we don't even know that we don't know. That's the human condition. We're finite beings trying to understand an infinite reality. We're temporary patterns of matter contemplating eternal cosmic processes. We're small creatures peering into the vast. And despite all that, we've made remarkable progress. We've pushed back the boundaries of ignorance. We've mapped the territory of the knowable. We've built tools that let us see the birth of galaxies and detect the ripples in space-time from colliding black holes. But the map is not the territory. The model is not the reality. The equations are descriptions, not the thing itself. The universe exceeds all our descriptions. It's always more subtle, more complex, more surprising than our theories suggest. Just when we think we understand it, shows us something new, something that doesn't fit, something that forces us to revise. This is humbling, but it's also wonderful. It means the adventure never ends. It means each generation gets to experience the thrill of discovery. It means no matter how much we learn, there's always more to learn. The universe is an infinite gift, and the greatest gift is that we can never fully unwrap it. There's always another layer, always another mystery, always another frontier. So we proceed with curiosity and humility. We build better tools. We make better observations. We refine our theories. We acknowledge what we know and what we don't know. We hold our beliefs lightly, ready to revise them when new evidence arrives. And we remain open to wonder. Wonder is what drives science. The sense that the universe is strange and beautiful and worth understanding. The feeling of awe when confronted with the vastness of space, or the depths of time, or the elegance of a mathematical equation that describes how reality works. That wonder is what makes us human in the deepest sense. We're not content just to survive. We want to understand. We want to know why. We want to see the patterns and comprehend the laws and feel connected to the cosmos. And the universe rewards that curiosity. Not with easy answers, but with glimpses. Not with final truths, but with deeper questions. Not with closure, but with endless opening. The mystery is the gift. The unknowing is the treasure. And you get to be part of it. Right now, somewhere in the universe, light is leaving a galaxy. Maybe it's one of those impossible early galaxies James Webb found. Maybe it's a galaxy we'll never see too far beyond our cosmic horizon. Maybe it's a galaxy in a universe nested inside a black hole in a reality we can't access. That light begins its journey. A photon leaves the surface of a star, travels through the galaxy, passes through intergalactic space, and heads out into the cosmic dark. It will travel for billions of years. It will pass through expanding space. The fabric of space itself will stretch as the universe grows, and the photon will stretch with it. Its wavelength will lengthen. Its energy will decrease. It will redshift from blue to red to infrared to radio waves. It will drift through voids between galaxies. It will pass through clusters of galaxies. It will witness the birth and death of countless stars, the formation and merger of countless galaxies, the slow evolution of cosmic structure over eons. And billions of years from now, long after you're gone, long after your species is gone, long after Earth and Sun are gone, that photon might land in a telescope. A telescope built by beings who don't exist yet. A civilization that hasn't emerged yet. On a planet that hasn't formed yet. Orbiting a star that's currently just a cloud of gas and dust, not yet collapsed, not yet ignited. Those future observers will point their instruments at the sky. They'll collect ancient photons. They'll analyze the light and decode the message carried across cosmic time. And they'll discover something. Maybe they'll learn about the era when galaxies formed impossibly fast. Maybe they'll see evidence of processes we never imagined. Maybe they'll find clues that answer questions we haven't thought to ask yet. Or maybe they'll find something that shatters their understanding. Something that forces them to rethink their cosmology. Something that reveals how much they still don't know. And the cycle will continue. Discovery leading to questions. Questions leading to new observations. Observations leading to revised theories. Theories opening up new mysteries. The universe isn't finished surprising us. It's just beginning.